So just before we start, I want to say hello, everyone. As always, this seminar series is co-sponsored by P41 Funded Center for Mesoscale Mapping, housed here at Martinos Center, and we're going to have Susie presenting the speaker today.
Hi, everyone. Welcome to BrainMap. It is a great pleasure to be introducing Horace Zhang. He is a fifth-year Ph.D. student at Yale, working with Gigi Galeana. His research focuses on image and contrast encoding with nonlinear gradients. And he did his undergraduate degree in engineering physics at Tsinghua University, during which time he worked with Cowan Setzenpop on an internship project. I think focused on wave encoding, maybe, or
actually temperature mapping with propeller EPTI.
Okay, yeah, temperature mapping with propeller EPTI, and then he came to Yale, where he's been working with Gigi on developing nonlinear gradient technology for diffusion MRI in the prostate and other body parts. So yeah, we're really pleased to have Horace here, and yeah, without further ado, here's Horace.
Okay. Thank you, everyone, and I'd like to thank Susie and Jason for inviting me. It's really good to be here. So this is the first time I've physically been here, but spiritually, I've been here before. I did my remote internship research with Kevin in my junior year of college, remotely in 2020. And after that, I've been working with Gigi Galeana at Yale University on nonlinear gradient coils, which is a concept that has been developed in our lab since around 17 years ago, developed by Jason, Gigi, supervised by Todd. So gradient nonlinearity has always been a headache for MRI, but here we are making use of it. So imagine a nonlinear field with locally strong gradient. I guess the most exciting and prominent application is the diffusion-weighted image. So I would like to start my talk by introducing a nonlinear gradient coil that is fitted between the legs for prostate cancer DWI, as well as its other use cases such as mesofiber microstructure imaging. And then I will talk about a more general topic, which is spatial encoding. And I would like to especially introduce the FRONSAC imaging and its linear counterpart wave, which a lot of you are familiar with, as well as the efficient mapping of dynamic nonlinear field. All right, here is the first topic of prostate DWI. So I guess for this audience, I don't have to emphasize the importance of strong gradient for DWI. The short T brings high SNR, that makes the short T2 compartment visible, and faster readout reduces this distortion, and we can also see finer microstructure with it. So the most prominent whole body gradient would be connectin to connectin 1. It has shown promising results not only on the brain, but also below the neck, but it's expensive and it requires comprehensive system updates and necessitates a narrow bore. Head-only gradients have been gaining attention, such as connectin 2 and GE from Magnus. They generate stronger gradients with a smaller radius, but they're usually permanently or semi-permanently installed on the scanner. Single-sided gradients is another direction that is gaining attention. So they are usually organ-specific and generate strong gradients over a limited field of view. For example, with the butterfly gradient coil that is developed in Western Ontario for a carotid application, and the breast gradient coil developed in Freiburg that can generate a locally strong gradient up to 1 Tesla per meter. So the motivation of this work is the prostate cancer DWI. Prostate cancer is the second leading cause of cancer-related death of men, at least in the US, and it features slow progression, so it requires early detection and active surveillance. Multiparametric MRI is a cost-effective tool for cancer screening, where DWI is the dominant contrast for diagnosis, despite its low resolution and low SNR, because it is sensitive to malignancy. The decreased luminal space and increased epithelial volume appear bright in DWI and dark in ADC. So this is the prototype of the inside-out nonlinear gradient coil that is that was designed in our lab and manufactured by Tesla, the company based in Storrington, England. So it is housed in a cylinder that is narrow enough to fit between the legs, and it features lightweight, flexibility, compact layout, and generate a locally strong gradient of 200 to 500 millitesla per meter for typical prostate locations. And because of the limited spatial coverage, it offers higher efficiency and lower inductance than whole body gradients. And this table is some properties of the gradient coil if you're interested in it. So this is how we are going to apply the nonlinear gradient channel onto the DWI sequence. I want to note that this is only for diffusion weighting, not for spatial encoding. So you can see that the nonlinear gradient is only turned on during the diffusion sensitizing block, and it shares the same timing with the linear gradient channels. So how does it look? This is the DWI of linear gradients, long T, p-value, a uniform p-value map from 50 all the way to 3000. You can see uniform signal decay brought by the diffusion contrast. And with the nonlinear gradient, you can see a non-uniform p-value map, but we can generate the same p-value at the prostate location, or again from 50 to 3000, but with a much shorter TE. And you can also see the DWI has non-uniform signal decay. So, of course, short TE brings brighter signal. Here are three questions to answer here. With a nonlinear p-value map, can we generate an accurate ADC map? The second question is, how much of an SNR gain does the short TE bring? And third question is, what about the lesion conspicuity from the short TE DWI? So let's dive into the first problem. How about the ADC? So this is the reference ADC map from the linear gradients with a long TE. The test ADC map from the nonlinear gradients, still the same p-value, but with short TE. You can see they are pretty much the same with the difference RMSE around 10%, which is a reasonable value for short-term measurement variation. Now, the second question is about SNR boosts. So the example SNR map intuitively shows the SNR boost brought about by the short TE. And this box plot is the average SNR of all the healthy volunteers and patients that we have scanned. And it shows a SNR boost by 26% from the median data here. So we are actually inserting this gradient, a nonlinear gradient, into the Prisma scanner, which features a relatively high gradient, 80 millitesla per meter. But for most common imaging sites, they only have scanners of 40 millitesla per meter. So we also test its SNR boosts on 40, 60, up to 80 millitesla per meter. So as you can see, the weaker the gradient is, the higher the SNR boost is. So it proves the necessity of the gradient insert for general clinical imaging sites. So about the prostate DWI and its lesion contrast, here's the patient that we scanned with a PIRADS 5 lesion, around 2 centimeters in the peripheral zone. This is the linear gradients with short TE, and this is a high p-value DWI. With nonlinear gradients, the TE is reduced, and you can see the prostate signal finally shows up. It's not drawn in the noise anymore, especially that the lesion stands out from the background. And the lesion location is further confirmed by the prostate ADC and T2 weighted image, but they do not show a contrast as good as the DWI. So this is the plot for all the patients that we have scanned. You can see a consistent CNR boost. The red dot is long TE, the green dot is short TE. So the short TE does increase lesion conspicuity, especially at high p values. For example, almost doubled 2,000 and you almost tripled at 3,000. Because the lesion tissues are associated with low ADC epithelial compartments. And I would also like to emphasize that the short TE does not only save the signal from the background noise, but highlights the cancerous short T2 compartments. So to to confirm that, we further look into the compartment model. This is the compartment model restriction spectral imaging that we chose. So it decomposes the diffusion-weighted signal into 4 compartments, from restricted diffusion, hindered diffusion, free diffusion, all the way to vascular flow. And their diffusion coefficient are predetermined. So we only need to fit the coefficient from C1 to C4. So this is the comparison of C1 all the way to C4 maps for long TE DWI and short TE DWI. So you can see that the restricted diffusion and hindered diffusion, they are highlighted by the short TE. Since that C1 is the hallmark that is acknowledged for implications of lesions, so we look into the C1 map and draw the contrast ratio boost of the lesion in the C1 map. You can see that they do have a consistent improvement. And so we can say that the lesion conspicuity benefits from reduced TE because of the short T2 compartment of restricted diffusion. So for now, I have talked about the advantage that is brought about by our nonlinear gradient coil. So how did we make it happen? It does not come from magic. So buckle up, I'm going to talk about some physics and technical challenges that we had. So first, it's the safety issue here. So basically, this is the coil that is fit between near the pelvis, and we're going to pump 600 amperes onto it. People are going to get nervous. Is it going to be like a prostate cooker that burns the patient? Is it going to shoot out like a rocket? How about the PNS, which has been a concern for connection gradient? So let's address these safety concerns. First, PNS. Because of the limited spatial coverage, it has reduced PNS risk. And for the cohorts that we tested, there has been no discomfort reported, even with the maximum amplitude and the minimum rise time. This is the heating, the temperature against the duty cycle. There is theoretical risk of heating because human body straddles the coil and there is thermal contact. But in reality, TWI's duty cycle is only around 10%, so the temperature rise would be only 1 or 2 degrees Celsius. The heat is negligible. And also the amplifier will trip when the temperature is above 38 degrees Celsius, but that's still the body temperature. So even if it trips, it's still safe. Motion. So this is the vibration spectrum that we got from the chirp pulse. So you can see that there is no spike or resonance reported. So you don't have to worry that it's going to shoot out like a rocket. But there is vibration, especially on the coil and the flat platform. Acoustic noise. The maximum acoustic noise is around 60 dB, and that is way below the safety limit. So there is no excessive risk of acoustic noise. Now, starting from the safety issue, I'm going to talk about its EPI compatibility. So basically, this is a hunk of copper without additional shimming that is inserted into the scanner bore. So the background phenon field is bound to be homogeneous. It's evident from the 2 slices that we test. This is the slice that is closer to the gradient coil surface. You can see a huge inhomogeneity up to 300 Hertz. This one is nicer because it's farther away. And that's why the prostate will show huge distortion when it's close to the coil, as you can see from the contour between GRE and EPI. But this one is sort of nicer. So for more distortion closer to the coil, pop-up cannot really correct it. So we actually retrospectively distort the GRE field map to fit the EPI profile. But for this case, you can do top-up, no problem. The second consequence is the ghosting artifact because of the spatially varying background phenon field map. But you can see that it's basically insignificant because the ghost to signal ratio is still way below 3%. So we think that's manageable. We don't need additional correction for the ghosting artifact. Now, eddy currents is another huge concern. Actually, this is something that people always blame when you don't know how to explain it. But here we are we have built a very accurate model of eddy currents. So eddy currents does not only come from the imperfect waveform from the nonlinear gradient itself, but also from the coils that it couples with. So this is the example of a few dynamic eddy current maps that we measured. They're basically flat, but changing with time, suggesting it's the B0 eddy current, which is also known as the Larmor frequency drift. And it's also confirmed by the quantitative analysis of the principal component analysis, showing that the most significant component is the 0th order eddy current, and this is its time curve. So the temporary conclusion here is that it has strong coupling with the 0th order main field coil because the nonlinear gradient coil itself is the 2nd ordered coil. But it has negligible coupling with the 1st order linear gradient coils, or from itself if we ramp slowly. For now, we're using the 1.52 millisecond ramp, just like the Siemens gradient. And this is the model of the Larmor frequency drift that we built. You can see that it is a long-term eddy current, spans a few hundred microseconds. And if we pull out the Larmor frequency drift at the center of EPR readout and plot it against the amplitude, you can see that it's a linear model. So we can predict the Larmor frequency drift given any waveform. So what consequence does it have if we don't correct it? Well, the Larmor frequency drift is going to shift the image globally in the phase encoding direction, as well as the consequential aliasing artifact, because we don't have the matching coil sensitivity profile anymore. But if we apply the correct Larmor frequency to the analog digital converter, then we can correct it with no aliasing artifact. All right, so much for the physical details. I'm going to give a conclusion to this project. So the next step would be to have a gold standard validation with histopathology to demonstrate the short TE brought about by the nonlinear gradient coil. And we actually can do the automated registration with the for the histology maps and MRI. So from the prototype, we can actually design a more efficient coil. For example, more turns down the thigh that still fits the body, but has higher efficiency. And we're also considering migrating it to a wider bore, lower gradient scanners such as VIDA. So in conclusion, we introduced this inside-out nonlinear gradient insert for prostate DWI, and the short TE does bring SNR and CNR boosts. The nonlinear gradient map can yield an accurate ADC map, and most importantly, it's safe and convenient for clinical practice. So next up, I'm going to talk about the second use case of the nonlinear gradient coil for muscle fiber microstructure imaging. To do that, it's simple. We just need to put the coil, between the calves. And the motivation is that the skeletal muscle microstructure has implications for peripheral artery disease, which features narrowed arteries and ischemia of peripheral tissues. So although it's a vascular disease, it has strong connections with the skeletal muscle. And people usually acquire time-dependent radiodiffusivity curve to reveal the microstructure of muscle fiber. And here, a very prominent biophysical model is the random permeable barrier model, or PBM. It tells us the fiber size, permeability, free diffusivity, etc., from the long diffusion time STEAM data. But STEAM is known for its low SNR. With a strong gradient, we can have access to short diffusion time, which is achieved by oscillating gradient spin echo. Now, before we dive into it, there are actually two unique problems associated with the nonlinear gradient coil. The diffusion encoding scheme is not a pure spherical Q space anymore. It's more like an ellipsoidal shape. The second problem is the coil vibration, which I mentioned earlier, and that's going to cause tissue displacement, which leads to defacing or signal voids in the image. So here is the diffusion encoding scheme. So this is the diffusion encoding scheme that is stretched by the nonlinear gradient coil in one direction, but it has still limited diffusion weight in the perpendicular plane. You can see that it's inscribed by the purple asterisks and circumscribed by the orange asterisks. Their excursion is significantly different. So the limited diffusion weight in the perpendicular plane makes this encoding strategy not ideal. Instead, we propose the left-right DWI to use the ADC to approximate the radiodiffusivity, because we know that the nonlinear gradient coil generates a strong gradient in the left-right direction. And the muscle fiber is basically oriented superior, inferior. So they are orthogonal. That's why we can use the approximation. Now, coil vibration is another problem that causes inconsistent tissue displacement, and that is especially magnified by oscillating gradient waveforms. So you can see that with the nonlinear grain coil vibration, there is signal voids or defacing that occurs on the boundary of tissues. And in the case-based point of view, you can see that the spectrum peaks of these high-frequency voxels, they are shifted beyond the edge of the case-base. Now, even if you turn off the partial Fourier, there are still remaining signal voids and remaining sharp phase change. So, but just by turning off partial Fourier is not enough. Instead, we need to completely isolate the vibration. So to do that, we just lift the calf to isolate vibration, but we need the heel support and the thigh support to do that. So this is the setup of microstructure imaging of our nonlinear grain coil. And we have designed a series of waveforms to cover a wide range of diffusion time, from 2-cycle OGSE, which is up to 76 Hertz or 1.8 milliseconds, to 1-cycle OGSE, PGSE, all the way up to STIM, which is up to 1000 milliseconds. But I want to note that because of the short T2 of skeletal muscle, TE has to be kept low. So we make the TE under 90 milliseconds. And the nonlinear gradient amplitude, which is up to 300 millitesla per meter at calf locations, they are adjusted at each diffusion time to achieve a sort of uniform p-value of 500 on the sagittal plane. It's more uniform. So this would test the protocol on the in-house fabricated fiber phantom, and it has a known diameter of 17 micrometers. This is example maps of radial diffusivity. The bright part, free water. The dark part, fiber bundle. And we can get a time-dependent curve. Orange is the free water. You can see it's mostly a constant, which is in accordance with the room temperature around 20 degrees Celsius. Blue part is the fiber bundle, and the time dependency is expected, although we can see some discontinuity on the boundary of the waveforms. And we also compare our in-house OGSE sequence with the nonlinear gradient with the Siemens OGSE, but with the linear gradient. You can see that they have very similar results. So starting from this time-dependent radial diffusivity curve, we can do the short diffusion time fitting with the Mitra formula, which is shown here. And from the fiber bundle proton density that we got from the spin echo, we can estimate the fiber radius and diameter. So it has shown a good estimate of diameter of around 16 micrometers, and that's close to the 17 micrometers ground truth, also as the free diffusivity. So we have shown good results here. Next up, we have tested the same protocol on ex vivo porcine soleus and in vivo gastrocnemius of human calf. Again, they show expected time dependency, and the estimates of free diffusivity, they're pretty much as expected in accordance with the room temperature or the human body temperature. But the fiber radius is a slightly underestimated 23 micrometers. A good estimate would be like 40 micrometers. But that's actually as expected because the same kind of underestimation also shows up in the RPBM fitting. And it could be partially due to the intracellular slowdown. Maybe there are other reasons that we're still looking into. So the next step for this project is to study the implications of such protocols for peripheral artery disease. And the conclusion is that we have accessed a short diffusion time up to 76 Hertz with the nonlinear gradient coil. And we have shown good estimates of free diffusivity and fiber diameter. And this is some technical problems that we have worked around with. So limitation, of course, it has some limitations. For example, the imperfect waveform. The short T2 requires a short TE, so it does not accommodate many cycles of OGSE. That's why it cannot achieve a very perfect frequency distribution. And there are discontinuities on the waveform boundaries. Also, the scan time is pretty long, so we might need to consider undersample the diffusion time to affirm efficient clinical scan. All right, so far about the diffusion encoding. The final part is about the spatial encoding, which is a more general topic. So theoretically, anything that is not main field or the linear gradients can be categorized as nonlinear gradient coils. For example, the second order spherical harmonics that is shown here. But more generally, in reality, they are often manifested as a linear combination of these theoretical fields. The slope of the field is, of course, nonlinear, and it's not even unidirectional. That's why it cannot be interpreted by k-space. We need to do the algebraic reconstruction, solving for ax equals y. And there are ambiguous pixels because it's no longer, it's a non-bijective mapping between space and frequency. So you may want to ask, why do we still need it? Well, there are still some merits. Tailored region of interest, varying spatial resolution, accelerated acquisition, and reduced PNS. So the most intuitive way to apply nonlinear spatial encoding is to apply it in the frequency and the phase encoding channel, represented by padlock. So in padlock, the phase contour, the phase evolution contour would be like this. So you can tell from that it has better resolution on the edge, but worse resolution in the center. And for the ambiguous pixels, it is solved by parallel imaging. The next version is more like projection encoding, which is represented by O-space imaging developed by Jason when he was at Yale. So this method focuses on the complementary encoding capabilities of receiving coil and the gradient coil. And to do that, it simultaneously applies the linear gradients and nonlinear gradients during the readout so that it can create a series of radial fields that has different center voxels, which is translated by Gx and Gy. And O-space outperforms radial, sense, and padlock, especially at high undersampling factors. Now, the most up-to-date version is the oscillating nonlinear gradient, which is represented by FRONSAC, and its linear gradient counterpart is wave, which a lot of people are familiar with. So the direct consequence of the oscillating gradient is its voxel spreading effect in the image space, which is comprised of a lot of distinct ghosts. Now, why do we prefer it? Well, we can explain it from the k-space point of view. The local k-space stamp is not a single point anymore. It's more like a smeared stamp that is able to acquire more information beyond that point and able to fill the gap that we might skip. From the image point of view, we can create different point spread function for each voxel, and that helps that benefits the identification in the de-aliasing process. It also brings additional merit to image reconstruction. Before, we need to use an entire bulky encoding matrix and iteratively solve the ax equals y problem. But here, we can drastically simplify the reconstruction with the PSF concept, which is also used in wave-Kuiper reconstruction. So the set-wise PSF reconstruction is equivalent to block diagonalizing the encoding matrix. That's why the computational burden is pretty much simplified. Now, it's really good to see that similar concepts are being developed across many institutes in the world. So this is the multi-frequency wave using multi-coil shim array developed by Birkin, Jason, Kevin. This is in 2020. And this is the fringe field of a plug-and-play gradient insert at Utrecht. And they play the ultrasonic waveform. And so they call it silent MRI here. At Max Planck Institute, Klaus Scheffler invented spread spectral imaging with an 8-square loop binaural coil array, which is also using a similar concept. So now we have come into an era of multi-GPA scanners, which is represented by sigma.x. because of the multi-GPA property, it has opened more opportunities of nonlinear spatial encoding. So the question is, how do we make it practical? I think there are two aspects of it. First, we need to perform an efficient mapping of the dynamic nonlinear field. We can't without spending 20 hours on it. The second one is we need to analyze the encoding capabilities of FRONSAC and wave and to see if there's an advantage of combining them. So first, I would like to start with a very brief introduction on the existing field mapping methods. The most intuitive one is, of course, the dynamic field camera. No extra scan needed, but it's not commonly accessible. A very typical way, single contour projection and extrapolation was invented by Zhang, by recording the dynamic phase trajectory of one contour and extrapolate it to the whole field of view. Voxel wide scan, which is the most rigorous but the most time-consuming method, also implemented by Jason in his work. So it turns off the readout encoding and adds an additional dimension of phase encoding. That's why it adds up to such a long scan time. Also, I would like to emphasize another trajectory auto calibration also developed by Stephen Colley in MGH. It uses the prior knowledge of sparse frequency distribution of the wave PSF. But it's impractical for nonlinear field because we have to do this optimization for every single voxel, and that is not computationally acceptable. That's why we need to develop an efficient mapping of dynamic nonlinear field. So here in our method, we estimate the point spread function, which is the direct inverse Fourier transform of the phase dynamic trajectory that we need. So it is based on the insight that FRONSAC has a few distinct goals. So the point spread function is now mostly comprised of the discrete spikes, while the other components are almost zero. So that's why the PSF is now formulated as a Kuhn function. We need to extract the corresponding voxels and fill the PSF. And you may want to ask, what about those pixels that are overlapped by the ghosts? Well, we have parallel imaging. All the receiving coils share the same PSF. So if you have a multi-coil Cartesian image and a multi-coil FRONSAC image, well, you can solve for the overlapped pixels. So this is the main idea of the proposed field mapping method. The other steps include the extrapolation to the edge voxels that is not covered by the mapping pattern, which is very important in the undersample reconstruction. So how does it work? This is the result from the proposed field mapping, which is almost the same as the rigorous field mapping. Very similar and low RMSE, but this one only takes half an hour compared to the 10-hour rigorous field mapping, and that is even with the low resolution. The half an hour is mostly spent on acquiring the fully sampled Cartesian and FRONSAC images. And of course, it comes with a limit. The intuition is that the ghosts cannot be overlapped too much. So with a fast oscillating waveform like FRONSAC, the ghosts are distinct. So you can estimate the PSF pretty well, which is suggested by the yellow difference curve 0. Now, with the frequency going down to the regime of wave, it's slowly oscillating, but the ghosts are very heavily overlapped. That's why that's the case you cannot estimate the PSF pretty well, as you can see from the crazy yellow difference curve. Okay, now so far about the field mapping. Now I want to talk about the encoding capability of FRONSAC and wave. So the encoding capability of wave is mainly determined by its amplitude rather than cycle number. That's why we need a high amplitude, but restricted by the slew rate. You need to go with a low cycle number because the performance is dominated by the maximum excursion in the k-space. FRONSAC, on the contrary, it needs a high cycle number, but with the slew rate, it can only go with low amplitude. And the reason is that for those insufficiently encoded regions, we need inhomogeneous orientations at adjacent k-space points, and that benefits the de-aliasing process. And also, it avoids dephasing. So there is merit in combining them. Of course, they are complementary, as you can see from the waveform and the voxel spreading effect. It has more voxel spreading than wave, so we can get more information from here. And this is the result from comparing wave and FRONSAC-wave. This is the reference. FRONSAC-wave is encoded with C3, S3, and Z2 nonlinear gradient channels. So this is a very high undersampling factor. You can see that wave has some details that is covered by the aliasing artifacts. But FRONSAC-wave is still can be recovered. And more intuitive comparison is the G-factor map. So whether it's the maximal G-factor or the mean G-factor, FRONSAC-wave has the advantage. And this is further confirmed by this curve, which is plotted against the undersampling factor. So 4 curves here from Cartesian FRONSAC-wave and FRONSAC-wave. FRONSAC-wave has a constant advantage, especially at the high undersampling factors. So in conclusion, we have proposed the efficient mapping for dynamic nonlinear field and drastically reduce the time. And FRONSAC-wave can further reduce the G-factor, but with no risk of PNS. Now, limitations. As I mentioned earlier, the field map of the edge focus are really important for the undersample reconstruction, but they're really hard to get. Even with a spatial polynomial extrapolation, it tends to exaggerate in the edge voxels. So that's probably the reason why the image improvement is not as significant as the G-factor improvement. And we need the oversampling of the readout. So it can only go with low bandwidth, but it risks distortion. Also, the set-wise PSF reconstruction is not compatible with the pseudo-random undersampling such as compressed sensing. With compressed sensing, you still need the entire bulky encoding matrix, I think. All right, so to recap my talk today, I have walked you guys through the diffusion encoding and spatial encoding, about prostate cancer detection, the short TE boosts SNR and CNR in the prostate cancer detection, and the microstructure, we can go up to a very high frequency OGSC waveform and have a good estimate of fiber microstructure. Spatial encoding, I have introduced the new mapping strategy, as well as the FRONSAC-wave encoding that benefits the general spatial encoding. And with that, without all the support from my colleagues, mentors, and collaborators, this work would not have been done. Nala used to be a research scientist in our lab, and she is now a assistant professor at Children's National Hospital. Jeffrey Weinreb is the creator of the PIRATS, the standardized scoring system of prostate MRI. And Todd and Gigi are very instrumental mentors. And I would like also to mention that Dimitri and Els, they always bring fresh insights into the biophysical model that we're using. And that concludes my talk today. I'd like to take questions.